Chapter 12.4. In this unit, you will learn to find the unit tangent vector at a point on a space curve and different components of acceleration. The first concept you'll learn is the unit tangent vector, which is basically the derivative of a function over its absolute value. The only condition is that the derivative of that function must not equal to 0. In other words, the function must be smooth on that point. Recall that in order for a curve to be smooth, its derivative must be continuous and non-zero in the interval. So in order to find the unit tangent vector of the curve given by rt equals ti plus t squared j when t equals 1, we find the derivative of rt, which in this case is I plus 2tj, and then the absolute value of its derivative, which is the square root of 1 plus 4t squared. Then, to find the unit tangent vector of the function, we simply multiply the derivative of rt, which is I plus 2tj, to the absolute value of the derivative, which is square root of 1 plus 4t squared. In the end, we plug in t equals 1 into the unit tangent vector, which results in 1 over square root 5 times I plus 2j. The next example asks us to find the unit tangent vector of a parametric equation given by rt equals 2 cosine ti plus 2 sine tj plus tk at the point t equals pi over 4. To find the tangent line, we utilize the same method, where we first find the derivative of the function, which in this case is negative 2 sine ti plus 2 cosine tj plus k, and then multiply it to 1 over the absolute value of rt, which in this case is square root of 5. Then we simply plug in t equals pi over 4 into the unit tangent vector, which results in 1 over the square root of 5 times negative the square root of 2i plus square root of 2j plus k. As the question asks for the set of parametric equation for the tangent line of the helix, we use the direction numbers that we just found, which is negative square root of 2, square root of 2, and 1, and the point that we find on the graph, which is square root of 2, square root of 2, and pi over 4, to derive the three parametric equations for x, y, and z. The next concept that we will learn is the definition of principal unit normal vector. If we assume C to be a smooth curve represented by R on an open interval, and its unit tangent vector does not equal to 0, then its principal unit normal vector will be the derivative of the unit tangent vector over the absolute value of the derivative of that unit tangent vector. In this example, where we have to find the unit normal vector for rt equals 3ti plus 2t squared j, in order to do that, we will first have to find the unit tangent vector of the function, which, as you may recall, is the derivative of that function over the absolute value of the derivative of that function. In this case, it is 3i plus 4tj over the square root of 9 plus 16t squared. Then, in order to find the unit normal vector, we would have to take another derivative of the unit tangent vector. After finding the derivative, we find the absolute value of that derivative, which is 12 over 9 plus 16t squared. And finally, we put the derivative over the absolute value of that derivative, which results in negative 4ti plus 3j over 9 plus 16t squared. Finally, we plug in t equals 1, which gives us the principal unit normal vector, 1/5 times negative 4i plus 3j. Then we arrive at the final theorem of this chapter, which is the acceleration vector, which is the vector that lies on the plane determined by the tangent vector and the normal vector. So in order to determine the tangential vector of acceleration, we either multiply the tangential vector to acceleration or divide the velocity times acceleration by the absolute value of velocity. To determine the normal component of acceleration, we either multiply acceleration function by the normal vector of the function, or divide the absolute value of the cross-multiplied velocity and acceleration by the absolute value of the velocity. Finally, in order to find the acceleration vector, we add up the tangential component of acceleration and the normal component of acceleration. In this final example, we are asked to find the tangential and normal components of acceleration for the helix given by rt equals b cosine ti plus b sine tj plus ctk. So we first find the velocity of this function by taking its derivative, which gives us negative b sine ti plus b cosine tj plus ck, and then we find its absolute value. We also get its acceleration function by taking the second derivative of rt. To find the tangential vector of acceleration, we basically plug in the values to the formula given earlier, which is basically the velocity times acceleration over the absolute value of the velocity, which gives us a result of 0 for the tangential component. Now, as we know the absolute value of the acceleration, which is b, and also we have determined the tangential vector for acceleration, we can use an alternative formula for the normal component of acceleration, which is the square root of the absolute value of the acceleration squared minus the tangential vector for acceleration squared. In this case, it gives us a result of b. And that is it for chapter 12.4. Please make sure you subscribe to our channel, smash the like button, and comment below any questions that you have. Thank you.